I'm the person who has come in sort of mid-distance. Right? We've had all the English speakers. We've had this speaker from Scotland. I'm come about 1,000 kilometres, and we've got people who've come damn sight further than that. We'll talk later. It's been 37 years since I first met you, and when I got the job in Sheffield as a young animal behaviour lecturer. I'd just come from France, where I'd spent 6 years in the CNRS in Gilles, working on fish behaviour and fish physiology. So I'd done some electrophysiology, but not very much. And I was mostly interested in these fish that I'll tell you about in a second, electric fish from South America. There was a whole lab in the CNRS that worked exclusively on them at every level, from anatomy, physiology, electron microscopy, behaviour, and so on. So in 1978 I came, and it was a new beginning for me, a completely different experience coming from a French research lab with practically no contact with students at all to the extraordinary and extremely stimulating atmosphere of the Sheffield Psychology Department at the time. Paul Dean has talked about the powerful influence of the Frisbee and Mayhew explanation in lay terms for idiots of David Miles' ideas and the whole systems approach to well, in their case, to visual perception. That obviously Pete took this on board incredibly in terms of his approach to neuroscience. Not that we called it neuroscience, then we called it psychobiology. That's right. Yeah. It's a trendy term, neuroscience, which is right. Almost immediately, I formed this friendship with Pete, and I've put a few of his. These are the adjectives which I think have already been mentioned by many people. Right. Generosity. I mean, it's not just generosity to colleagues, but to students and everything. To us personally, it was just quite extraordinary. We were waiting to move into a house we'd bought, and the owners refused to give us the key for a month. So Pete and Jill just said, okay, we'll put you up in our house. It was absolutely, as far as they were concerned, sort of normal thing that you do. At the time, our kids were 3 and 1. They're now 40 and 39. That really does make you feel a bit old. And so, he just, thought it was a completely normal thing. We started talking a lot about the science, about what I was doing, what he was doing, and you've heard from Paul Dean and from Phil Wynne in particular, the background that he had by 1978. Another word which has been mentioned once is teetotal. I'd never met somebody who was teetotal. He actually didn't drink alcohol, and it didn't cause him any problem at all. If you went to the pub together, Pete was more extrovert, more excitable, and generally having a much better time than most of the people who were thinking they were disinhibiting their nervous system, but in fact were, on the whole, falling into bad behaviour in many cases. Also a biker. This is something that Pete blames his hearing loss on, is that the sound of wind in his helmet. And I had the honour of, I think it's the only time in my life I've ever been on a motorbike, of travelling through Sheffield and back. So this is my sort of first impression of Pete. I was appointed in May 1978. I started my teaching in the autumn. And for those of you who remember the politics of the time, this was a seriously bad time to be in Sheffield, or in anywhere for that matter. The fall of the Callaghan government, the unions had decided to push the Labour government for wage increases. The Labour government said, you must be joking, it's completely impossible. The economy is accepting massive strikes. The winter of discontent brought Thatcher to power, and the world as we knew it then, completely changed. Thatcher, Reagan, miners' strike, mass privatisations, the world changed. This meant that me and Pete spent a lot of time talking about politics, which we always did over sandwiches at lunchtime. So this was a sort of a habit that was set in very early on. We always ate together, listening to the World at One news on Radio 4, commenting from our somewhat divergent political perspectives a lot of the time. One of the things about coming to Sheffield, well, you've seen a lot of these old pictures before. I didn't take any of the ones off Google Images, but here's what Pete looked like in 1978. That's what I looked like in 1978. Lots of hair, lots of beards. Again, there's John Frisby. You won't find Mayhew here because Mayhew refused ever to go to anything like a final year photograph. The tutorials were great fun. We did quite a lot of them. And there was a certain person in my very first year tutorial called Paul Overton. And this was quite a shock to me. It was extremely hairy, as he's already shown. I haven't got a picture of him, but Paul was brilliant. And I thought, my God, I am really going to be out of my depth if this is what Sheffield students are like. Luckily, they weren't. They weren't all like you. There were lots of very good. And of course, Paul went on to get a first, eh? Yes, and he did extremely well. I think he was the best student in that year. So these were the people that I was up against. In these tutorials, first year tutorials, second year tutorials, third year tutorials, again, as Paul Dean has pointed out, we had a lot of freedom. We could do what we wanted, basically. You didn't have to teach your own topic. I did do a lot of animal behaviour stuff and behavioural ecology things and stuff related to my lectures. But because of our lunchtime discussions, Pete had infused me into the importance of the basal ganglia, dopamine system, self-stimulation. I always used to give a tutorial on two visual systems, which Paul mentioned, Schneider's two visual systems. Very important. And slowly I was getting, I thought this is actually quite interesting. However, that's not what I was there for. I actually spent the next 10 years working on electric fish, and incredibly briefly, because that's not what I'm really going to talk about. These are what electric fish look like, some of them. These are South American ones. Eigenmania, the very same as Gymnotus carapo, the two that I've worked on. Basically, these fish have an electrosensory system that they use for detecting objects in the environment. They're all nocturnal, and they create instantaneous electric fields around their bodies, and they can sense the distortions in those electric fields by using a bunch of special electroreceptors, which were actually discovered in the lab I was in France previously. And they can sense distortions in this electric field. And this has all sorts of fascinating things, like how on earth can you actually generate impulses this short. There's nothing terribly surprising about the impulses of Gymnotus carapo, a millisecond, but there are many species which can produce pulses right down to 100 microseconds in duration. I can remember one absolutely classic referee's comment I had, which was, what you are describing is physiologically impossible. There is no known physiological system that can produce an electrical output as short as 100 microseconds. Do you know how long a synaptic delay is? Well, unfortunately, they do, and they've been doing it for millions of years. Now, my PhD actually had been on I started off from saying if these fish can detect their own electric fields, then they can detect other fish's electric fields. So do they use this for communication? The answer is they do. And I went on to do a whole bunch of stuff, which I'm not going to really explain in much detail, but we discovered, for example, that there were sex differences in the electrical discharges, that these sex differences were to do both with the frequency, the Fourier power content of those signals. They were also to do with the actual waveform, so males and females of certain species could produce different types of pulses. You can do a lot of very nice experiments with electric fish. Basically, they've got externalized nervous systems, essentially. So you can record these discharges with electrodes that you just put in a fish tank. You can play back pulses to them with artificial fish like this, just a dipole like that. And the fish behaves. You can with the superb help of the technicians at Sheffield at the time, Chris Brown, who was just absolutely brilliant, built all this equipment for me, which allowed me to generate pulses which you could modify all the polarities, phase relationships, and so on. You could show, for example, that they could identify the head, the tail. They would approach, they would show courtship behaviour, they'd show aggressive behaviour, and so on, depending on the characteristics that you play back. The sort of studies that people have done in great depth on bird communication. It has a lot of very important theoretical things, because we showed, this was the last paper actually published on electric fish in '92 with Peter Redgrave, who's a bird behavioural ecologist at Nottingham, where he's now in Scandinavia somewhere. We showed, for example, that we had groups of up to 50 of this species. Each fish had individually characteristic waveforms, and every single fish in paired studies was capable of identifying individually those species. And they could do this on the basis of minute differences in the ratios of the different phases. This has theoretical implications. How on earth does the fish's nervous system do this? And with Carl Hopkins at Cornell, we did a whole lot of studies which showed pretty conclusively that the way they do it is that they synchronize their discharge rates in such a way that they can scan very slowly through the pulses of a neighbouring fish. So if you imagine, I mean, this is a simple computer simulation, just a single cycle biphasic response. So this is one fish, okay? So you stack together all the pulses that he's producing. And here's another fish in the distance, smaller, okay? If they're very close in repetition rate, very close to what you see on the oscilloscope screen, if you trigger from this one, is you see this pulse slide through the other one. And as it slides through it, it modulates the amplitude of this one, but it actually spreads it out over time, which gives the nervous system enough time to analyze its characteristics. Okay? And you can, experimentally, you can mess about with blocking this scanning, increasing the scanning, speeding it up, doing whatever you want, to show that actually they can't do it if they're not able to scan through these pulses. That is all very exciting stuff. I lived and breathed it. Also got funded to do 2 massive field trips in South America, which is a great experience. You know, this is in French Guiana. Of course, being able to speak French is fantastically useful because France has colonies and it's kept all over the world, which are actually part of France. You know, French Guiana is a department of France. So, you know, there are French biological stations in the rainforest. So this was my study area, Papinabo Creek, and this is some of the amazing kit that Chris Brown and the technicians produced for me to take out there, which allowed me to. I mean, this was state-of-the-art stuff. This was at the time, right? This was long before digital memory recording and stuff. So Chris wrote a whole mass of software which allowed me to record on digital tape. You know, this is like the early versions of video recorders, and also to do playback experiments in the field. And so, you know, I've got a nice paper there which is, you know, pretty well cited. That was the 1980s, basically, for me. One of the things about electric fish is the media loves it. Right? It is almost better than anything they can imagine. Here's a weird animal that communicates in a weird way. So the BBC got on to me very early on, Oxford Scientific Film. So if you actually go back and watch the DVDs of Life on Earth, Living Planet, Super Sense, there's about 10 things that I was involved with where they actually paid for us to have, Marion will remember, to have you know, the big predatory electric eels in the lab, and they paid for the whole lot. You know, so, and then complete nutters like Bellamy, who's now, I looked him up actually preparing this, and he's gone off the rails completely. He's gone like Francis Crick. He's now a global warming denier, and he's 85 or so now. I was on his show, which was quite fun. Anyway. Pete, you always used to say, you know, this is all very well, but or something like this, you know. Pete really relentlessly kept on working on me, and I think Paul to some extent as well, although he never really said anything. It's usually fire Pete. So basically in 1986, so I lasted in this lonely world of electric fish. I was the only person in the country working on electric fish, so I had no collaborators and students, but that all worked very nicely. So Pete said, you've got all these skills, surely we can just transfer them to electrophysiology. And already, as Paul Dean has pointed out, there was a lot of behavioural stuff. There was all the work on microinjection, dopamine systems, and so forth going on in the lab. So here's the team in 1986. Who probably, that's me then, already gone white. There's Marion, who's there, and Paul, Safa, Pete again, and there's Natalie, who's here. She's hardly changed a bit, that's what I think. Don't know if any of the ladies are there. Right, so basically what I did was, I mean, I'd already done some electrophysiology on fish in France, but I hadn't done any research. So basically, I just converted myself into an electrophysiologist. We haven't got any electrophysiology equipment, so we built it all ourselves. And I think in those days, it actually was so incredibly expensive to buy. And our technicians were so skilled, and we had sort of 4 people in a workshop who did all sorts of stuff, but they built the whole thing. So I spent about a year or so setting this up, you know, the whole stereotactic thing, vibration damp table, floating on go-kart in tubes, all worked extraordinarily well. And so we set up basically the electrophysiology to study what Paul has already described, the 2 major descending pathways from the superior calicus. Now, by this time I actually knew quite a lot about the superior calicus, so I've been teaching it to students and had a lot of discussions with Pete, and so, you know, we were beginning to really get to grips with some of these things, and so there were a lot of electrophysiological questions that were raised. So it was a very powerful team, if you like. We've got behaviour, pharmacology, anatomy. Pete was then developing all the fancy anatomical techniques. And I then I went to Paris again and spent a lot of time with Gilles Chevalier and Deniot, Jean-Michel Deniot, who gave me a lot of insights into how they'd done their studies on the double inhibitory systems in the basal ganglia. So I gleaned quite a bit of information from the people. Right, the first paper, where it was actually a presentation, that I ever published with Pete was at the EWCBR meeting in Tignes-les-Bruyères. Now, for those of you who don't, it still exists, this meeting. I don't know if anybody's ever been to it. It's like the World Economic Forum in Davos, basically. It's just an excuse for people to ski. The scientific sessions take place, I think they start at something like 7:30 in the morning and go on till 10. You then go out on the slopes and you come back when it's dark, right? So, and then they have slalom races for distinguished scientists. So the spin-off of this meeting, which is in Tignes, was that I learned to ski. And again, generosity has to be the word, it has to be attached to Pete. I couldn't ski, I was totally useless in terms of almost any sport, really. And he said, it's easy. So I spent one morning with him, and he just devoted himself to teaching me how to ski. And by the next day, I managed to ski. I looked up the ski piste map. 1,500 meters I skied down from l'Aiguille Percée, which is, the midpoint up the thing, or the Aigle Percy, as the English call it. So that was really pretty impressive meeting, and it was the first time I actually started interacting with these neuroscientists with our first data on the characterization of these two pathways. So we really were beginning to get a feel for the sorts of stimuli that would activate these two descendant pathways. And that became part of this paper that Paul Dean's already mentioned, Event or Emergency, which is still way up in citations. If you look that up, it's easily my highest citation, 400 and something the other day. Yeah. So, and people refer to it very, very frequently. I think it was quite a groundbreaking thing. The electrophysiology also, I feel, was, we in some senses just go back to that a bit, we somehow set the scene for the electrophysiology in the lab. When I left, which was 13 years ago, Véronique Croiset basically took over, had already started taking over from me. And she was then using some of these results that me and Pete found. Basically the first electrophysiology me and Pete did together. And we discovered, for example, this what is now being used in Paul's recent paper, this visual sensitization of deep layers with bicuculline injections, which we discovered sort of serendipitously by sort of messing about, injecting bicuculline, looking at this inhibition of responses and so forth. So I then, was part of the team, and we did really quite a lot of stuff, which I'm pretty proud of. Right? These are the major papers. I think the output pathways, which show different sensory properties depending on, without going into any details, most of you know what all these are. The other thing which hasn't been mentioned so far is the cerebellar influence. And again, we managed to show this convergence from the deep cerebellar nuclei, the excitatory input from the deep cerebellar nuclei, converging on the basal ganglia input from the substantia nigra. This is again probably the last paper I had anything to do with, which was Veronique's. When I Monique's latest papers. And we did various behavioural stuff by injecting bicupulin directly into the superior cuticles. We also did quite a lot of stuff with microwires in the chronic recording of microwires in the superior cuticles, particularly with Hong Ying Wang, who's now in Toronto. Okay, in 1993, I was given the chance of moving into humans, and this really was a fantastic opportunity. Ros Mitchell, who was then the only female neurosurgeon in the country, invited me to go. She's married to Ian Mitchell, who used to work in the group. And I worked with them solidly for pretty well 7 years, being the electrophysiologist in the operating theatre particularly for thalamotomies and pallidotomies. At the time when we started, deep brain stimulation hadn't really got a hold in the UK. So we were blowing holes in the GPI. To decide where to blow the hole was rather a tricky business. So these are some of my recordings so we were recording down the track that we were eventually going to lesion with. So we were recording with the lesioning electrode. One of the things to try and avoid is the optic tract. You lesion the optic tract, and the patient is not very happy about the outcome of the pain. However, what really decided me that that's what I wanted to do was just in these awake patients, seeing the effect of completely removing, as I pressed the button on the lesioning generator, watching their tremor disappear. It's one of the most powerful things. Patients classically used to burst into tears. They couldn't believe it was possible, because we used to have them. They had their hands held out with an accelerometer fixed to their hands. You lesion and it stops. And they just say, that's just incredible, I can't believe it. And it works. It just really does work. Later on, we started developing the STM, deep brain stimulation, and that was basically what I did. Spent about a day a week doing that. In 1997, I was pushed very hard by John Frisby to run the teaching quality assessment. And this is where Pete's famous question is, what do you want me not to do? Sort of came up, and as he said to me, what do you want to do that for? And I don't know why I said yes, really, but I did it. And with the enormous help of Julia Poole, we managed to fill a room full of bits of paper, produce policy documents on just about everything. We had to convince colleagues that teaching was not just teaching, it was about learning. You had to actually see what the students had learned. Anyway, John Frisby tried to persuade me to stay and become head of department, and I said, no, I didn't think so. And I'd already more or less decided that I was going to go. So in 2001, I took over retirement, went back that way, actually a lot further than Paris, to Birmingham. Spent about 3 years rebuilding the house, plumbing and wiring and stuff like this. And slowly but surely I thought I really ought to be doing something a bit more useful to the general public. So I went to Créteil, which is one of the neuroscience centres near Paris, Hotel Mondor, and started doing intraoperative STM recordings with the foot there. And this is Nguyen, who was the neurosurgeon at the time. He left. And then I thought, well, what am I going to do now? I'm going to go to somebody else I know quite well, and that's Yves Agid. Yves Agid, if you don't know him, this is the sort of top dog in French science. He is the most highly cited scientist in any domain in France. And he said, come work with us. So what I'm now doing is I'm working on Parkinsonian gait analysis in Yves Agid's group. Yves Agid is now retired. He's about 76 now, but the whole team is still there. What we were particularly interested in doing was looking at the effects on Parkinsonian gait of various manipulations, particularly deep brain stimulation, and also looking simultaneously with the neuroradiologists in this building about the associated brain lesions. Now, working on human brains, as you probably realise, is not at all like working on rat brains. They're much bigger. But actually, you are not allowed to do most of the things that you would like to do. So you have to wait for nature to take its course. Okay, so this is the ECM. I haven't actually put a picture of the thing from a distant view. It's modelled on the two cerebral hemispheres. This is the architect's idea. So this is the left hemisphere. This is the corpus callosum here. Right, and there's another block like this, the other side of it. Okay, it's a massive 80 million euro building, funded, and it's rather a sick joke actually, by the Schumacher Foundation, as in the racing driver, who is now, I think he's still in a coma, but basically he's fantastically interested in head injury. And he put millions into this as well. The fancy system we've now got is this Nexus system, which is the three-dimension thing that is used for motion capture systems. If you've seen Avatar, if you've seen Paddington Bear, they actually use the same system that we're using. It's basically massive cameras, infrared illumination, and computer reconstruction in 3 dimensions of the positions of limbs that you get from 5U saws that you stick on joints or wherever you want to put them. Parkinson's patients are not very happy about having these things stuck all over. So most of the stuff we've done has actually been on a force plate, which is a piece of metal which is about 2.5 meters long, meter wide, and it measures the ground reaction forces in 3 dimensions. And just to give you some brief coverage of some of the stuff that I've been involved in, we were interested in, there's STM, and this is nigra reticulata. So these are patients who've been implanted for deep brain stimulation in the subthalamic nucleus. We went through 200 patients to find ones where there was at least one electrode that was in nigra, so that we could actually stimulate what you're not supposed to do, which is nigra, and compare it with what happens if you stimulate STM. We only found 7 patients out of this cohort, but the results are very interesting. I haven't really got time to go into any of that. I can certainly talk to you about it later. But basically, STN seems to be involved in the control of locomotion parameters, and the SNR, particularly posture, balance, and a thing called braking, which if you watch how somebody walks, I'll just sort of try and demonstrate it. If you don't walk like a very poor robot, you actually break the fall of what's called the swing leg. Okay, so as you walk along, you put the swing leg goes out, and you break the fall. You break the fall by appropriate contraction of 2 main muscles: the anterior tibialis, which is the muscle down the front of your leg, and the soleus, which is the calf muscle. which are antagonistic. Okay? So this is a normal person, as this. And what you see, if you look at the vertical velocity of the centre of gravity of the person, is you see that it reaches a minimum about 200 milliseconds before your foot hits the ground. So what actually happens is you actively break the fall so that you have a smooth progression. And this is exactly what Parkinson's patients can't do. Right? They suffer from co-contraction, and we were recording from these muscles simultaneously. You get these muscles activated simultaneously at the point where they hit the ground. So Parkinson's patients walk with these stiff-legged petit pas where they don't go. So this was a very nice measure, and it turns out that this is something which we now believe is almost certainly peduncular pontine, and because in our latest study, which came out in December, this one, in Journal of Neurology, it would appear that the lesions that these patients have suffered are principally in the mesencephalic locomotor area region. And it looks like PPN may well be involved in that, and there's a dissociation between posture and locomotion. So these are our recent papers. So this was the biggest one, brain, and last year as well, the balance. Right now, I'm going to end up with something which you may think is totally irrelevant, and I thought it was totally irrelevant actually until relatively recently. Very quickly, a bit of bee behaviour. Right, you may know that when a beehive expands in the spring, it gets to a point where there's not enough room for all the bees. So half the bees, approximately, leave as a swarm. That's what swarming is, and they found with the old queen, and they form a new colony. There's a selection problem here, a really serious selection problem. They've got to get this right. If they get that wrong, the colony is dead. Right? They cannot survive. They've got to have a cavity to live in. And they don't mess about. They do it in two stages. So the swarm leaves the parent hive and it hangs, classically, in a tree or a branch or something, about 100 meters from the hive. And the colony sends out scouts to look for a final resting place. This is a democratic process, and there's a lovely book by Tom Seeley called Honeybee Democracy on this, which summarises all the research that's been done in the last 50 years. The bees go out and they vote, basically, by doing the famous dance that bees use to indicate the distance and direction of possible food sources and of nest site sources. So here are the voters, okay? They're all sitting there. They go out, find things, come back. Other bees are recruited and they go out and they look. And they come back, and then slowly you see a change in the behaviour of the bees. Slowly but surely, everybody starts dancing to the same location. Whereas earlier, you could have 10 or 15 different locations, holes in tree trunks and so on. And to take one of Pete's slides and to modify it slightly, this is what you could imagine. This is actually, it's something very similar to action selection. And you get the disorders in honeybee behaviour. Every now and again, they can't decide what to do. And they become akinesic. They actually don't move, right? So the initial swarm stays where it is and dies. It actually dies out, or if they're lucky, they might be able to survive if the weather's okay. Or they may split completely and become a bit like sort of schizophrenic problem, and you may get half the bees going to one place and half the bees going to the other. Okay, so the honeybee social organisation has often been likened to a distributed nervous system, and I'm interested to see that Kevin Gurney has now got some money to look at bee. Look at the bee brain in relation to these things. So there's this democratic selection and a voting system which is a bit like the voting system, which means that they're all saying we want to go to this place, and in the end a decision is made in the normal group, but every now and again it goes severely wrong. You might have to think about that, but not. Right, so basically I went from fish to rats to humans, and really is thanks to Pete, I think. A lot of discussions. The bees I don't think we had very much to do with it except in eating my honey. You stay with rats. Something that I do in my now extended spare time is to do metal sculptures. So the least I can do is to offer you a rat. Thank you very much.